This video is for section 17.2 about measuring and expressing enthalpy changes. The learning goals are be able to measure the change in enthalpy of a reaction and be able to express the enthalpy change for a reaction in the chemical equation. Let's look at that first learning goal. How do you measure the change in enthalpy of a reaction? Well, first, we need to know what the word enthalpy means. The enthalpy change is equivalent to the heat flow if pressure remains constant. In our textbook, all of the chemical reactions that are discussed in the book are assumed to happen in the context of constant pressure. Therefore, enthalpy change means the same thing as heat. The symbol delta H represents enthalpy change. And in the last lesson, we learned that the symbol Q represents heat. Since enthalpy change and heat are synonymous, delta H is equal to Q. If a system absorbs heat from its surroundings, then delta H is positive. The amount of heat in the system is increasing. If a system releases heat to its surroundings, then delta H is negative. The amount of heat in the system is decreasing. It is typical to use subscripts to indicate whether enthalpy change refers to the system or the surroundings. For example, the symbols delta H cis means the enthalpy change of the system. But if you see the symbol delta H surroundings, that refers to how the heat of the surroundings is changing. The word calorimetry refers to the measurement of heat flow into or out of a system. So the learning goal is, how do you measure the change in heat in a reaction? And the answer is with calorimetry. Calorimetry uses a device called a calorimeter. It's a device used to measure heat flow. There are two types of calorimeters. The first is a constant pressure calorimeter. And here's an illustration of one made out of a styrofoam cup containing water with a thermometer dipped in the water. Here's how this calorimeter works. Let's say you take a hot object and drop it into the water. The object will cool off, the water will warm up. Using the thermometer, we can tell by how many degrees Celsius the temperature of the water changes. And by knowing how the temperature of the water changes, we can figure out the heat loss in the piece of metal dropped into the cup. If we were still in face-to-face class, we would have done this experiment, where we dropped hot metal into a styrofoam cup and measured the temperature change of the water. Another type of calorimeter is a constant volume calorimeter. This is also called a bomb calorimeter. You can see that the device is a lot sturdier than a styrofoam cup. In a constant volume calorimeter, we actually burn up the substance that is put into the device. The heat from that combustion reaction increases the temperature of the water, which can be measured with the thermometer. By knowing how much the temperature of the surrounding water changes, we can figure out how much heat was contained in the substance that was burned. If we still had face-to-face class, we would have done a lab on this, where we burned up a piece of food. It's common to use a potato chip or a peanut, something that has oil in it, and so it burns up well. And by measuring the temperature change of the surrounding water, we can figure out how many food calories are in that piece of food. Recall the formula from the previous section and how we rearranged it to create a formula for heat. The same formula is used in calorimetry to determine the amount of heat flow in the calorimeter. This paragraph right here describes how you use a calorimeter. And I described this earlier in the case of the styrofoam cup calorimeter. Here's a check for understanding question. When 25 milliliters of water containing 0.85 moles of hydrogen chloride is mixed with 40 milliliters of water containing 0.05 moles of potassium hydroxide at the initial temperature of 23 degrees Celsius, the temperature of the solution will increase to 25.5 degrees Celsius. Hydrogen chloride is hydrochloric acid. Potassium hydroxide is a base. When an acid and a base are mixed, heat is produced. Enough heat to change the temperature of the water from 23 degrees to 25.5 degrees. How many kilojoules of heat is that? To find the answer, we'll use the formula at the top of the screen. Delta H, which means change in enthalpy or change in heat of the water, is equal to the mass of the water times the specific heat of water times the temperature change of the water. First, let's substitute for the mass of the water. There are 25 milliliters plus 40 milliliters of water in the calorimeter. That is a total of 65 milliliters of water. Every milliliter of water weighs 1 gram. So if there are 65 milliliters of water, then there are 65 grams of water in the calorimeter. Now we need to multiply by capital C, the specific heat of water. That was given in the table in the video in the previous lesson. 4.18 joules per gram degree Celsius. Next, we'll multiply by the change in temperature of the water. It increases in temperature 2.5 degrees Celsius. The canceling of labels looks like this. Grams cross cancels grams, degrees Celsius cancels degrees Celsius, leaving the label joules. On a calculator, we'll multiply these, and the answer is 679.25. The question asks us to give the answer in kilojoules, and we know the value in joules. To change from joules to kilojoules, you divide by 1,000, creating the answer 0.67925 kilojoules. This is how much heat is released in the reaction. The surrounding water gains this amount of heat. The reactants, that is the HCl and KOH, lose that same amount of heat. The next learning goal is be able to express the enthalpy change for a reaction in the chemical equation for that reaction. If you write the enthalpy change of a reaction in its equation, then you're writing a thermochemical equation. Here are some examples. Calcium oxide plus water produces calcium hydroxide plus 65.2 kilojoules of heat energy. Hopefully you recognize this equation looks like the equations you've seen all year, but it has this extra value added on, the enthalpy change. The next example, 2 moles of sodium hydrogen carbonate plus 85 kilojoules of heat would produce 1 mole of sodium carbonate, 1 mole of water, and 1 mole of carbon dioxide. This is a thermochemical equation because it has the component heat energy. Next, a question to connect today's topic to the previous. Which reaction above is endothermic? Which reaction absorbs heat energy? That would be the second reaction. The second reaction uses heat energy to make the product. Where does it get that heat? From its surroundings. Which reaction then is exothermic? That would be the first one. The first one releases heat energy. It produces as a product 65.2 kilojoules of energy. There is another way to write thermochemical equations. Here are the same 2 examples, but written a little bit differently. Calcium oxide plus water produces calcium hydroxide, and then notice how it says delta H equals negative 65.2 kilojoules. This is saying the exact same thing as this first example. The fact that the The fact that delta H is a negative number means the reactants are losing that amount of heat. I guess that means it was released into the surroundings. These delta H values written in equations are the heat of reaction for those equations. Heat of reaction is the enthalpy change during the reaction under the following assumptions: that the reaction is occurring under a pressure of 101.3 kilopascals and that the temperature is 25 degrees Celsius. If the pressure and temperature are not those values, then a different amount of heat would be absorbed or released in a chemical reaction. In our first example, what this equation is saying is that 1 mole of solid calcium oxide reacting with 1 mole of liquid water produces 1 mole of calcium hydroxide plus 65.2 kilojoules of heat. The second example has a positive delta H value, meaning that the reaction absorbs heat from the surroundings. So this equation is saying that 2 moles of this substance absorbs 85 kilojoules of heat from the surroundings to create 1 mole of each of these products. Here's a check for understanding question. A chemical reaction has this equation, and notice the delta H value on the side. How many kilojoules of heat are used to decompose 3.2 moles of sodium hydrogen carbonate? Well, the coefficient in the equation in front of sodium hydrogen carbonate is a 2. So this is saying that 2 moles of that substance has that delta H value. But what about 3.2 moles? Let's make a conversion. We have 3.2 moles of the substance sodium hydrogen carbonate, and we'll multiply by a conversion factor. 2 moles of that substance had this delta H value. On the calculator, go 3.2 times 85 divided by 2. The result is 136 kilojoules. Some chemical reactions are combustion reactions. These occur when one of the reagents is oxygen and the products are carbon dioxide and water. The heat of reaction for the combustion of 1 mole of a substance is called the heat of combustion. So heat of combustion means the same thing as heat of reaction, but this term is used when the reaction is a combustion reaction. Here's an example. Methane plus oxygen makes carbon dioxide plus water and has this delta H value. What's the meaning of this equation? It's saying that the heat of combustion for methane is negative 890 kilojoules per mole. Every mole of methane that's burned produces 890 kilojoules of heat energy. This concludes the lesson about enthalpy and heats of reaction.